I'd like to invite the next speaker to share his screen so we can continue. So this is Dr. Robert Rueger from SCM, who will be talking about the Amsterdam Modeling Suite and MOPAC's role in that.
Yeah, thank you for the introduction. Can you see my screen?
Yes.
All right.
Yeah.
Yeah, so I want to talk a bit about MOPAC in the context of the Amsterdam Modeling Suite, but I don't know if everybody is familiar with our company, so I thought I would first give a bit of an introduction. So the company is Software for Chemistry and Materials. It was founded in 1995 as a spin-off from the Theoretical Chemistry Group in Amsterdam. By now we're completely independent from the university, but we still have our office space in the university because we like to be close to the theoretical chemists. Our job is to develop and support this Amsterdam Modeling Suite and its flagship DFT code ADF. So in the past, I think the name ADF was much more prominent than Amsterdam Modeling Suite, or AMS as we go by these days. So this is how you might know us.
Someone's mentioning they're having trouble hearing you. Could you maybe turn up your volume or something?
Okay, I can try.
Yeah, I can hear you just fine, but I'm trying to be responsive to problems people are noting.
Is this getting any better?
Sounds
is it loud? Is it louder at least?
It's definitely louder.
Yeah.
Okay.
Yeah. Sorry about the disturbance.
Yeah, no problem. So this is the current team of SCM. We're roughly 20 developers, and it's growing around one developer per year. But we also have a collaboration with a fair number of academic groups that work within our software suite. So the connection between SCM and MOPAC and Jimmy Stewart is actually pretty old already. So we added MOPAC to our software suite in the 2008 release, I think. So that was way before my time, but I looked it up in the old changelogs when MOPAC showed up within our software suite. So technically there were two phases prior to AMS 2019. We were just shipping the MOPAC binaries as they are, and our GUI had support for using these binaries as an external program. So I think SCM was acting as a reseller for commercial users that wanted MOPAC, while it was free for academics. Correct me if I'm wrong with this, but I believe that's how it worked. So technically the second phase was then that with the AMS 2019 release, we fully integrated MOPAC into the AMS driver, which is our central piece of software. And in this talk, I want to show a bit what this actually means in practice and where the advantages of this are. So the AMS driver, let me first make a definition here. So within our software suite, anything that takes in the geometry of a system and then spits out energy gradients and possibly other properties, maybe like a dipole moment or a polarizability or something like this. Anything that does this as a black box, we call that an engine. So that's how we distinguish between the driver that moves the system across the potential energy surface and the engine that does these single point properties. So in our setup, we have the driver and the engine. So the driver is always what users run. It's the executable that in the end you execute, and it has all these things implemented that you expect from atomistic codes, like it can do geometry optimization, transition stage searches, MD, you name it. And on the other hand, we have these engines, which are their only task is to do these single point calculations when the driver demands it. And technically, these things are just libraries. So the MOPAC binary, that was the MOPAC exe. In our setup, it became a library in the 2019 release, and it's one of the libraries of engines that we ship. So we have ADF, which is our flagship DFT code for molecules, BAND for DFT for solids, and we have DFTB, but now machine learning potentials, reactive force fields, all different kinds of things. So these are all engines within the AMS driver, and it's also possible to have engines that contain other engines and nest them if you want to do some QMMM calculation with mechanical embedding or so. Then engines can be combined to form a new engine, basically. And the applications in the AMS driver, they can be pretty advanced. So let me just highlight one thing here, which we recently added, which we call the path exploration. So then what you would do is, I don't know if you can see my mouse pointer. I hope so. So you could put in a geometry and then basically tell the AMS driver, please go explore the potential energy surface from here. And it would try to climb up to nearby transition states and then go look at the minima on the other side. And then over time, it would map out would map out this graph here, basically, where you can see the different reactions that can happen in your system. So this is an application in the AMS driver, which is fairly advanced, but just so that you get an idea of what the driver could do for you. For users, this separation between the driver and the engine is also fairly obvious in the input. So this here is a legitimate AMS input file on the left, and you see that the entire green part is basically the input for the AMS driver. So that is says here that we want to do a geometry optimization, calculate normal modes in the end, and some details. Of course, you also have the system in there. And then there's a single block here in our input, which defines the model that you are using for the potential energy surface. So here we're saying we would like MOPAC with the PM7 model. So for the user, it's very straightforward now how you would switch out MOPAC to another engine. So if you wanted to go to a DFT, then all you would have to do is change here to ADF and maybe set some options for the ADF engine. So the separation between driver and engine is also very clear in the input. So if you look a bit under the hood, then so this is kind of the slide for developers. So on the one hand, you have these applications in the AMS driver, and on the other hand, we have this abstract class, which is just then the AMS engine that you interact with as a developer working at the driver level. And what you pass into the engine is just this description of what is the system and some object that tells the engine what it should calculate. So do you only want the energies, or do you need gradients, or polarizability, or something like this? So that would then all go into the engine, and the engine can actually then be one of these different things that we support. And when the engine is done, it passes a container with all the results back to the driver level that you can work with there. So for a developer working at the driver level, usually they don't have to care what engine is running under the hood. They get a similar interface from all of them. So in a way, this is a bit like the atomistic simulation environment, if you're familiar with this. So there you have these calculators and you're passing these atoms objects around. It's similar, but the performance in our setup, it can be on a different level, because we're doing everything within one binary. That's an MPI parallel program. So tricks that we can pull is that if we have parallel work to do at the driver level, say we need to do some numerical derivative or so and need to displace all the atoms in some direction, then all these things are independent, and we can actually split our communicator and then spawn multiple of these engines and let them do the thing in parallel. So I did that here as an example for MOPAC. So here we have a nice molecule, which are geometry optimization, for which I want to do a geometry optimization and then calculate the normal mode. So I first have this initial serial part of the optimization, and then there is this parallel part of doing all the displacements for the normal modes. And I see here that you get some parallel scaling. So we have 48 evaluations for the initial geo, so that's how often we called into MOPAC there, and then 564 for the symmetry independent evaluation displacements that we need to do for the Hessian. And of course, in a setup like this, the second part scales very well. So the limit that you go to here is the time for the initial geometry optimization that you cannot get further down at some point. Yeah, so this was what I wanted to say about the AMS driver. A nice usability feature that we also have within our software suite is that we have Python interfaces around the AMS driver, and then by extension around all of its engines. So there is this PLAMS library, which is also on GitHub. The official acronym is the Python library for automating molecular simulations, but it might as well be a Python layer around AMS. So here's a little script that shows how you could load a molecule And then you would basically set up this input, the text input file that I showed in the previous slide, by saying you would like a geometry optimization and that you would like to use MOPAC. And you can just run your job and access results in a relatively convenient way directly from Python. So you can get the energy and the optimized geometry here, which I use in this little example. So this is available then for all engines because it's going through the central AMS driver that the Python library interacts with. We also have our GUI, which I mentioned in the beginning. For this, I just wanted to show a little demo. So this is what it looks like. Let me use one of my favorite molecules for these kind of demos. Here we can select that we would like to use the MOPAC engine and that we do a geometry optimization with frequencies. And I think that's all I would like to set here. Let me save this job and run it. So there we got our, oops, already come to the front. So we got our initial geometry optimization, and then here we have the second part where all the numerical displacements are done for the hashing, and then we get we can look at the trajectory of that the optimization took in AMS movie and see how the system changed in the optimization. This one did not change very much. And we can also visualize the IR spectrum that we just calculated. Okay, let me switch back to slides. So that's pretty much all I wanted to show for the GUI. So I think it's time to wrap up already. So the point I just want to make here is that by having MOPAC integrated as one of the engines in the AMS driver, there's a lot of these engine agnostic features that you get for free and that just work out of the box then. So any new task that is added to the AMS driver, and it's a couple in every year's release, is immediately available from MOPAC 2. And in general, once you're in the suite, there is a relatively nice connection between the different engines. So you can, for example, easily do things like let MOPAC calculate an initial hashing that you would then use as to kick off a transition state search with a DFT engine, or you could use MOPAC as the QM or MM region in a mechanically embedded QM/MM calculation. These kind of things that combine engines. Yeah, and you also get this scripting through PLAMS and the GUI integration pretty much for free. Yeah, this is all I wanted to say. I think we're open to collaboration. So anybody who has some ideas and wants to work with us, you're always welcome to visit in Amsterdam. And I think Jimmy has done that in the past. So do let us know.
All right, so now there's some time for questions. Does anyone have any questions? I had a question or two. Here, I can ask a question while other people maybe think of questions.
Sure.
So when you say there's this MPI layer, so MOPAC itself is not MPI parallelized, but it's able to run multiple instances of MOPAC on different MPI tasks simultaneously to gather information independently from different calculations. Is that what's going on?
Yeah, indeed. So in principle, the MPI communicator, you can split it at the top level, and then the MOPAC engines they could work on different systems. If you don't do that, then just the same system is passed into the engine, and since then MOPAC is not parallelized with MPI internally, there would be duplicate work that would be done on all ranks. And we did actually go in there and replace some parts of MOPAC with a call to some MPI parallelized linear algebra library. So the diagonalization where it happens, then actually you would get some speed up there also inside of MOPAC, but those are just a few parts that we sped up in this way.
I see. Yeah, and so the open source MOPAC is kind of set up now as mostly being a shared library. with the main executable calling that shared library, so that there may be a room for coordination here, so that like
yeah, that's also what I thought when I saw your talk. So when we did that, I think it was clear to us what the future of MOPAC would be. But of course, if there is continued development on MOPAC now, making this library interface to it is not too much work. So we should definitely hook up to the open source MOPAC.
Yeah. So maybe I'll reach out to SCM in the future to see if we can coordinate that.
Yeah, definitely.
Okay. All right. If there's no further questions, we could move on to the next speaker and stay on schedule.